All right. So, how was your convoluted experience? Okay, so let's see what you did. Can I use the board?
Using this one?
Thank you. So, so that one was easy, and we talked about it, and I hope now you understand what you did. We took something that had sharp edges. We took a smoothing function, a smoothing kernel that looked like that had a bell curve shape, and then that helped us smooth our function with the sharp edges. So we don't have sharp edges anymore. All right. Cool. If you have any questions about that, ask me. I'm here until midnight. Make sure that everyone is comfortable with this. All right. Then the second one. Let's see what you did. You took a noisy function, and then what color should I use? And then we took a kernel that is equal to 1 between 0 and 10. And then we multiplied our function with the kernel point by point, and then summed it up between 0 and 10, which basically means I'm doing a sum of my function from 0 to 10, right? And then what did we do? We divided by the kernel sum, which means we divided by 10, right? So basically, with this convolution, what we did was that we averaged our function f over a window of 10, and we put the value at the center of my interval. All right? And then I started sliding it one by one, and then I repeated that, and that gave me the average of my function over the whole interval, right? Now, why do we have why did we define our vector to be one of the shape of our function to be 1, 1, 10? It's because in PyTorch, in general, what you can do is, so let's imagine an image, right? So in your image, you have a two-dimensional matrix, which is your image, right? And then you have red, green, and blue layers, right? So we have several layers, and then every layer you can have a two-dimensional matrix. So the convolution can be applied to much more complicated forms of input. Another thing you have in the exercise when you go home, work on it, is that I have asked you to define a function, whatever function you like, your favorite linear function, and then add noise to it. So plot your function, see how it looks like, and then add noise to it, and then repeat this exercise again. It won't teach you much about convolution. It's the same as what you did here. I just want you to keep remembering everything about PyTorch that you have learned so far, about how you define functions, how you add noise, how you do convolution. So do it at home and come back with questions if you have questions. That's the optional thing that you have in the Colab. All right? So done with this part. Let's move on to the next. We want to do convolution in 2 dimensions because both images and documents, languages, you can look at them as, oh, do we need to turn this? All right, meanwhile, did I answer all of the questions that I promised to answer? All right, good. So usually we deal with 2-dimensional matrices. And to make it very easy, let's just assume that the 2-dimensional matrix is an image that we want to work with. Now, for a 2-dimensional matrix, we usually deal with 2-dimensional kernels. And kernels in 2 dimensions are matrices with some numbers in them, similar to what we saw in 1 dimension. So this is a 2-dimensional matrix that we want to apply. We want to apply to my 1, 2, 3, 4, 5 by 5 matrix. All right. So I have an image. This is my image, and I would like to convolve it with this kernel. All right. What I do is, so remember the values are 0, 1, 2, 2, 2, 0. So what I do is that I take a piece of my matrix and I do element by element multiplication of the values of my matrix with 0, 1, 2, 2, 2, 0, 0, 1, 2. Okay, so the small numbers are the values of my kernel, and the big numbers is my image. All right, so I multiply them one by one. I get one number, and I sum it up. So I have 3 plus 4, 7, plus, this is all 0, plus 1, 8, 8 plus 4, 12, right? And I put it here at the top, right? Then I shift my kernel by one by one element here to the right. All right. Then I do element-wise multiplication and then sum it up, and I put it here. It happens to be 12 again. So I'm here. I have one more to go. I shift it again, and I do element-wise multiplication, and I sum it up over here, and I get another one. Then I shift it down and repeat until I get to this point where I cannot move anymore. Okay, so this is like a game. You slide, multiply, sum, and you get one number. And then slide, multiply, sum. This could be another T-shirt. Yes.
What's the reason of applying convolution on a picture?
We'll get there. We'll get there.
Okay.
The why is very interesting because we can do so many different things with convolutions. For example, I have an image, and I can use convolutions to find edges in my image. All right, and we will see how. And you will do it here today. Yes.
So does the kernel always have to be the smaller of the two arrays? And if so, how small can you go?
It can be, so if it is just one, it will be a scalar. It's useless, right? It should be greater than 1, bigger than 1. So at least start by 2 by 2, and then move around.
also.
Yeah, you can't even move it, right? Unless you pad it, and we'll see what it is.
How do we handle audio signals?
Uh, how do we handle audio signal? You build a spectrogram of your audio, and it becomes a two-dimensional thing, and then you do stuff with it. So you take the Fourier transform, and you do a bunch of other stuff, and we can talk about it after this if you like. All right, now this is everything that I told you in a GIF format. The shaded, the gray thing is my kernel. The blue thing is my image. And so I do this, multiply element-wise, sum, and I put it in the corresponding pixel. And this is my convolution. This is what I get after doing that. Is it very clear? Isn't it more easy than one dimension? Yeah? See, that's why we go to higher dimension. Sometimes increasing the dimension makes things much better. Yes?
Yeah, I have. So basically, you're aggregating one area of that image, right? So then this becomes like a dimension reduction technique? Can it be? Because you are like what someone said, you're doing feature selection. It's just like applying like layers to aggregate to like to a.
If you look at it that way, you can call it, but this is not traditionally called dimensional reduction. But you can take an image and summarize it into things that are that have much less pixels and contain some information. But it's yeah. All right, and as we saw, everything can be written as matrix multiplications. This thing that I showed you here, you can convince yourself that if you call the elements of the kernel, if you call them W, you can represent this, what we are doing here, the convolution. You can represent it by a massive matrix and multiply it by your image and get the convolution that way. So we are back to matrix multiplication. You see, it's everywhere. All right. So far it's clear in 2 dimensions, everything. Now the problem is when I start here, I always end up with a smaller dimension, right? And then I have to deal with the edge effects. So if you think about it, this pixel here, I see this pixel here only once when I do this, right? Because here is the only time that I see the information in this pixel here, right? But these other pixels, they are visited more than once, right? Now, how can I solve that? I will augment my image by adding zeros to it, okay? And it's called padding. So I add cells here, and I fill it up with zeros. So this way. So here is padding by 1. And if you remember in the hands-on that you just did, we had padding equals 5. That was because our kernel was 10 units long, right? So I added 5 to each end of it so that we start from 5 before, and we can align the 0 with the 0 of the function. All right? So when we pad, we repeat that exercise again But now the first one has zeros in it, and then I shift it. I shift it in. As a result, my convolution will be a larger matrix. And here I have padding of 2, and this is how I compute the convolution. Cool? And you see the result is also bigger. Any question up to here? All right. Now we know padding. Let's talk about strides. So far, in the previous case, we were sliding our kernel by one component, by one pixel, right? But it's not necessary. It's not necessary to pick the slide to be only by one step. We can make it jump by 2 or 3 or 10 or 100, and so that's called stride. And in PyTorch, that is another. So padding is one of the inputs to the convolution that you provide. Stride is another one. And you can pad and give it a wider stride. So that's a combination of both.
How do we choose the right stride length?
This stride length, there should be some way of doing it. Well, it usually is given by, I would say, the correlation between your pixels, because if you so think about what you're doing here, right? You're taking all of this patch and combining into one pixel, right? If your pixels are correlated, if let's say every 5 of your pixels are correlated, super correlated, then you're not actually gaining much information by going one by one, because there's a huge overlap, and you can make your stride wider to go beyond the correlation length. That's how I think about it.
It's also less computationally intensive if you have a very, very big image.
Yeah, and but you have to pick it wisely, because if you take wide strides, if they are too big, you're losing information, right? If it is very small, you have duplications. So you need to pick something in between, and that something in between is given by the correlation length in your signal.
Did you talk at all about how you choose the size of the kernel?
I didn't, but I think when we get to the example, we will talk about that. Yes.
So if you look at the one below, the dashed lines, would those have weights?
The dashed lines, they
Yeah.
have zeros in them.
Oh, okay.
Yeah, so the values, this is the padding part, right? And when we pad, so the dashed lines are filled with zeros. Okay? Okay, too easy, right? The other thing is something that you hear in the same context, but it's not. It's actually a layer usually in the network. It's called pooling, and I think you have all seen max pooling, min pooling, average pooling, mean pooling. So that is when you have when you have a two-dimensional matrix or n-dimensional matrix, and you see that this is too big. I don't really need all of this information. Maybe I can thin it and I can downsample it. So to downsample it, what you do is that you take something which is very similar to a kernel. So you say, I take slices of this, and I look at the slice, and I decide which one I want to pick here. Okay. So for example, there is max pooling, where I pick a slice, and I say, maybe all of the information that I have here is given by the biggest pixel here. So throw away everything else, keep the big one, and give me that. And then I pick a stride of 2, so I shift it here, and I do the same thing, and the biggest number here is 8, so I keep that one, throw everything else away, and do it here and here. All right? So that is called pooling. You can do max, you can do average to make sure that you keep everything here, or you can be creative. You can come up with your own. You can use a linear function to do that. So that's pooling. And usually what you do is that you do convolution, you do something to your input, and then do some layers, and then your dimension increases, and then you have to deal with this massive matrices, and it's expensive, and you don't want to pay, and it's useless to pay all of those GPU time costs, and you downsize your sample here, your result, and then you work with it, and it works. If it doesn't work, then you have to change your parameters. How do you do that? You find the right size and stride and everything else for your problem. So look at this one and tell me what kind of pooling have I done here? Yeah? What?
Speak louder, guys.
I can't hear you.
Max pooling.
Thank you. This is max pooling.
Harriet said it first.
All right. How do we do it in PyTorch? I haven't put it in the hands-on part. I'm showing you here. If you like, you can copy, put it in the Colab notebook. But it's very simple. Let's define a max pooling of 3. What is 3? So 3 is the size of my matrix. And then, so it says use max for pooling in 1 dimension. So I'm going to apply it to 1-dimensional data, and pick the length of my pooling to be 3, and use a stride 2 of length 2. Okay, so jump. And then I define the input to be a random number of size 20. And this is the tensor that is created. Then I apply the max pooling to that, which means it takes the first 3 and looks at the maximum. What is the maximum here? 0.87, right? So that puts it here, and then and jumps by 2. So it takes this. What do we expect to get? Maximum of these, 1.99, and that's how it works. Yes.
So what's the NN before the max pool there?
Oh, NN is in PyTorch. You have this object, a class called NN, which has all of the neural network utilities in it, and this is one, and you use it for. All right. Any question about pooling? Yes.
Just with the convolution of 1D, one-dimensional, we're talking about function, but with the two-dimensional, we don't talk about function anymore, or is it just image as a function?
No, it's a, well, image is a two-dimensional function.
I see.
Yeah.
So like a function of the intensity, like
Function, no, intensity is the value of the function.
yeah.
So it's a function of the pixel numbers. So in pixel number
Coordinate.
2 and 5, you have the intensity of 11.73, right? That's how you look at it. And for audio, you have time steps, and you have the intensity and everything else in the audio that you have. And for NLP, you have words and where they are. And you embed the words into higher dimensions. And you have a bunch of vectors at every point. And the order is important. All right, so this one, yes.
In NLP, when we apply convolution on a text, what happened to that text? And as a visualization, I mean. For example, if we have, this is a book, and when we convert it to some vectors and apply this convolution, what will happen? In image, I can understand you can change the contrast of some part of the image, and you can recognize the edges. And what will we gain from that text to applying this convolution?
It's very difficult to visualize it that way, but basically the vectors contain semantic information, right? And when you have a text, the words that you're putting together, if you're sure. So if you're writing something, you have a coherent concept that you're writing about, and so your text follows a semantic relationship between all of your words. You can compare it to an image where when you have a face, all the pixels in your image where you have the face, they are correlated and they are related to each other. And so when you do convolution to a text, you can assume that it's taking the semantic information and it's extracting things for you.
Highlight some part of the text, yes. To distinguish on that part, for example.
Yeah, I can't, bless you. I cannot visualize. Why don't you try it and let us know?
Okay,
So
take. I can say, so when you use convolution as opposed to neural net, you get a holistic view of the text that you're convolving. So if you have 3 words, 4 words, whatever, so that works usually very well for multi-word term extraction to understand, oh, this is a cohesive piece of text, as Amir said earlier. And that's what it does. Without that, it's not that sensitive to order anymore.
Yeah, and that's why if you, thank you, and that's why if you have if you have information in your text, and usually you do, that for which the order is important, the sentence is important, where you don't only want to extract key phrases or concept, you need to not to use convness. You need to use something that conserves the order in your text, and that's why you do LSTM and some flavor of RNN.
Convolution on that can do topic modeling then, right?
Kind of. Let's take it offline.
Yeah, let's take that up.
Yeah, but let's not forget that. What's your name? Reza. Reza will take a text, will convert it to, you will use pre-trained word embeddings, and we'll build a two-dimensional matrix that visualizes that text and will show us what it looks like. All right? And then he will do interesting things with it using convolution and will show us what it does. All right? Cool.